In the previous podcast, I explained how olives are crushed and the most common methods used for doing so. In today's episode, I'll tell you what happens to the olive pulp once it comes out of the crusher. Hi, this is Milena. Welcome back to Olive Oil Drops, the first podcast entirely dedicated to olive oil and olives. This podcast is created by Marco Antonucci. This is an English version. To obtain juice, it's quite obvious that the fresh fruit must be crushed, ground, or pressed in some way. This is true for oranges as well as for olives. In fact, many consumers imagine that to produce oil, olives are crushed with huge granite wheels called millstones, which rotate on a round stone or metal base to form a pulp. This pulp is then spread on special filters and placed in a press that compresses them, releasing the oil. Only about 10% of the oil mills worldwide still use this ancient system. The principle, though, remains the same. The olives are first crushed and then pressed. In the modern process, an intermediate step has been added between crushing and extraction, the malaxation of the olive paste. The term comes from the machine that performs the task, the Malaxer. Now, the Malaxer's function is simple but super important. It prepares the mixture for the next step, when the oil is separated from the pulp and water. Malaxation consists of slowly and continuously stirring the pulp inside the machine so that the small oil droplets can merge into larger ones, which can then be more easily separated in the following phase. It also breaks up the natural water-oil emulsion that forms during crushing, because the tiny oil droplets struggle to combine on their own because they are surrounded by a lipoprotein membrane that keeps them emulsified. The slow mechanical movement of the malaxer combined with the action of the enzymes, which are naturally present in the olives, breaks this membrane and helps the droplets merge. After malaxation, over 80% of the oil droplets typically reach a size greater than 30 microns, essential for easy separation in the next stage. Now, the malaxer basically consists of a tank. Imagine an enamel bathtub from the 70s with an inlet and outlet on opposite sides, usually horizontal. Inside, a central rotating axis, we can technically call it malaxing shaft, continuously stirs the paste coming from the crusher. This is similar to what happens in a mixer, but instead of a hook or a flat beater, there is a kind of worm screw, a peripheral coil welded to the ends of perforated radial profiles. These are angled with respect to the central shaft to create a bidirectional push, keeping the paste in motion, ensuring continuous mixing and maintaining contact with the temperature-controlled walls. Essentially, the outer spiral pushes the paste toward the outlet, while the inner blades, mounted in the opposite direction, bring it back. The inner blades usually have large holes to improve mixing. Now, some models also include angled elements or unique geometries designed to enhance performance. At the end of the spiral, larger blades often press the paste towards the outer hole. The design of this component is critical because its shape affects yield, temperature stability, energy consumption, and mechanical wear. A malaxing shaft that merely stirs the paste is useless. The rotation speed is usually quite low, around 15 to 30 revolutions per minute. The tank is closed with a sealed lid, often with glass panels, so we can check what's going on inside. Many models include built-in lighting for better visibility. It may seem obvious that the tank should be sealed, but until about 30 years ago, malaxers were often open, without any closure system at all. Some models still on the market use dense metal mesh or slitted panels instead of a tight seal, allowing the paste to be seen during processing. In any case, it is essential that the malaxer operates with the lid closed, both for safety and to protect the oil. As explained in the podcast 14, air suffocates oil. We are not kneading pizza or bread where air is desirable for yeast activation and dough expansion. We are working with olive paste, which is rich in fatty acids that are sensitive to oxygen and easily oxidized. Malaxers are made of stainless steel. The tank usually has a double wall through which water circulates to control temperature. The operator sets the desired temperature on the control panel, and an automatic system circulates hot or cold water as needed, either from an internal heater or from an external gas boiler. Malaxers can be horizontal or vertical. The main difference, aside from size, is the paste exposure to air. In horizontal machines, the contact surface can be up to 100% larger. Other differences include ease of cleaning, the number of moving parts, and whether partial filling is possible. There are also inclined malaxers, mostly for experimental use but not for commercial purposes. The size of malaxer can range from 70 to 80 kilograms for small mills to over 6 tons for industrial ones. The number and size of malaxers depend on the mill's capacity and the desired malaxation time. Small mills often use only one malaxer, while larger facilities typically use 2 or more, connected in a series or in a parallel depending on their process. Now, the effectiveness, yield, and quality of malaxation depends on the type of olive paste used. Difficult pastes are always more challenging. Beyond paste type, factors such as the shape of the paddles, oxygen control, duration, and temperatures are all fundamental. In upcoming podcasts, we'll look at how these parameters influence results and how to set them correctly. Temperature control is achieved through a special jacket around the machine through which water at desired temperature circulates. Typically, processing occurs within a fairly narrow temperature range, roughly 20 to 30 degrees Celsius. Now, oxygen control or management is a bit more complex. Originally, malaxation tanks were open, allowing the paste to be stirred in direct contact with air and with any dust or contaminants it carried. This essentially replicated what happened with traditional millstones. Later on, the first protective grids appeared, followed by fully sealed lids. It was eventually understood that oxygen affects both the paste and the oil. Even in a full malaxer, there is always a small airspace at the top. At first, producers try filling the space with nitrogen or other inert gases that don't interact with the olive paste. Many modern malaxers still include systems for injecting these gases. Then later on, it was discovered that a small amount of oxygen is actually beneficial. This led to the development of systems that carefully limit air exposure using automatic filling sensors and modified machine shapes to maintain only the minimal required airspace. Today, these systems are common, but new technologies are emerging. One promising innovation is high vacuum malaxation, a process used widely in the food industry. It involves vertical malaxers operating under vacuum conditions around 0.2 bars, maintained by vacuum pumps and safety valves. There are also new experimental systems that may one day replace traditional malaxers, technologies using microwaves, megasound, and protoreactors, which we'll discuss in future podcasts. If you have questions for us, you can ask us any question at oliveoildrops@gmail.com, website www.oliveoildrops.com, where you can also find texts of this podcast both in Italian and English, or a comment space of the podcast platform you have been using and to which you can subscribe free of charge. Thank you for tuning in.